At this point, we know that reactions happen, we know what a chemical change is, we know how to balance reactions, we probably even know how to predict products pretty decently. We know the patterns of reactions, we know the different types of reactions. But what we want to talk about right now is sort of how reactions happen, a little bit as to why they happen and some of the other things we notice, but mostly how a reaction actually happens, what's going on at the molecular level. And for that we need the kinetic molecular theory, which is I'm shortening to KMT. Now KMT, or kinetic molecular theory, is something you probably already kind of know something of from other things that you've learned. So for example, all matter is made of particles because, particles are in constant random motion. And that's going to be kind of important. And that the distance that those particles are able to travel is going to depend a little bit on the state that they are in. So for example, solids, where they're all packed in tight, they can move quite quickly, but they can't move very far. So they can wiggle back and forth. We call it vibrate. Liquids have that kind of motion as well, but they can also kind of rotate, they can spin. Sometimes they can move a little bit left or right. And gases, they've got these large spaces between them, so now they are able to actually move, the term is translate, through space. Now I really want to point this out. If I have a solid, liquid, and gas all at 70 degrees Celsius, they might all be moving very quickly, but gases are the only ones that we're going to notice moving around because of the amount of space that they have available to them. Well, that takes me back to this other thing, that temperature is related to the average speed. So if I heat things up, the particles move faster. They don't necessarily move greater distance, but they're definitely going to move faster. So going back to my solid, liquid, gas at 70 degrees Celsius, those particles might have all the same rough speed, but gases, of course, are going to be moving a whole lot further, so we're going to notice that more. Okay, getting back to my main key question is, like, how does a reaction actually happen? Well, let's take this reaction, a very simple reaction, and break it down. If I look at that reaction and I represent my reactants as diatomic atoms, or diatomic molecules rather, as spheres joined together, I start out with things that look like this, and I finish with those things, the products. Now, it's a simple addition reaction, or a synthesis reaction, I guess I should say it. If I look at it in terms of more of like a Lewis diagram kind of thing, or a structural diagram, I end up with that. Hydrogen bonded to hydrogen, iodine bonded to iodine, but then hydrogen bonded to iodine, and hydrogen bonded to iodine, which I normally put as a 2 in front, right? Okay, so what that means is, even in a very, very simple reaction, two things have to happen. Number one is I have to break bonds. I had to break the bonds between the hydrogen, I had to break the bonds between the iodine. Bonds need to be broken. Okay, new bonds need to be formed. So the hydrogen had to bond to the iodine, and that happened a couple of times. So I need to break bonds, I need to form bonds. And I can do something like that for almost anything. In some cases it's not bonds between atoms, it's the attractive force between an electron in a metal, for example, and the nucleus, and then that electron gets lost. So that's not a bond, but that attractive force needs to be overcome. Okay, so how does that happen? Well, a bond, kind of like the example I was using with the electron being attracted to a nucleus, the electron of atom number 1 is attracted by the nucleus of atom number 2, and vice versa. I've got two atoms attracting that pair of electrons simultaneously. That's the bond. They're sharing those electrons, but that sharing means that both nuclei, positive charges, are attracting both electrons, negative charges, and both of them are trying to do that, so they end up sharing the electrons. If I'm going to break that bond, I'm going to need to overcome that attractive force. That is going to require energy. This is going to be really, really key, because it's also something that's a little bit counterintuitive. We've kind of learned that if I break bonds, I release energy. Maybe you've learned that. That's wrong. If you break bonds, you require energy. Energy has to go in. On the other hand, the similar thing would be true in reverse, that if I allowed things to come together that are attracted to each other, energy is going to be released. So forming bonds releases energy. So anytime I break bonds, I usually have a corresponding bond formation happening somewhere else in the products. That is where the energy release comes from. Now, I'm going to pause here just briefly and introduce something that we'll talk about, excuse me, talk about another time. If I only have to use a little bit of energy and I get a lot of energy back, I'm going to notice the energy coming out. On the other hand, if I require a lot of energy but I only get a little bit back, I'm going to notice I'm constantly dumping energy in. So this notion of, well, how do I have both when I only notice one? I notice the overall. Anyway, where does that energy come from? If I'm going to put energy in, if I'm going to get energy back, where does it come from? And if I'm going to require energy to break those bonds, it's going to come from the motion. So these particles are in constant random motion. They're going to be colliding with each other all the time. And when they collide with each other, the energy that they had in their motion can get dumped into the bond. It can basically shake the bond a little bit. And so what happens is if I shake that bond enough, if I take that motion energy and I dump it into the bond, I can actually break that bond. Now, bond energy is generally considered to be storage. If you've done physics and you've talked about kinetic energy, motion, and potential energy, energy and storage, in chemistry, that stored energy is in the bond. But if I dump a bunch of energy into the bond, I can break it. Okay, so now I've got this balance between potential energy and kinetic energy. And if I have enough energy getting dumped into that bond, as I mentioned, I can break it. So my collision, if I want to have a reaction, I have to have that collision, key part number one, and that has to have enough energy to break the bond. Too easy. Okay, but there's more to it than that, of course. If I take this collision, all right, so I've got particles moving, this is still my hydrogen iodine, but if I take this collision here and I have them collide, can I dump energy into the bond? Sure. But let's compare it to this one. If I have the second one, the bottom one, lined up, well, now what I have is my particles are lined up so that as those bonds break, the particles are in perfect alignment for the new bonds to form. Okay, let's look at it this way, just atoms and structures and stuff. If I collide those atoms together, or those molecules together, because it's 2 atoms per molecule, if I collide those molecules together, I can have this instant where I'm breaking the bonds between the hydrogen and the hydrogen, breaking the bond between the iodine and the iodine, but also the hydrogen and iodine are both perfectly lined up so they can start to form new bonds. I can have this moment where it's a bit of a mess, where bonds are breaking, new bonds are forming, other bonds are breaking while new bonds are forming. I'm not saying that this particular reaction happens in exactly this way. This is just the example I'm using, but it can actually happen that instead of bond breaks, bond forms. It can be this mushy thing where bonds are breaking while new ones are forming. But either way, they have to be in correct alignment. And if they're lined up right, then I can form the products. Well, what if I had that collision, but the bond's broken, the old bond's reformed? I'd never know it. So the only thing I'm going to notice is if new bonds form between new partners. Okay, let's revisit this. If I have a collision between particles and there is enough energy in order to break the bonds and they're lined up correctly, then I can have a reaction. Now the other thing that this means, or the other thing that I know, is that breaking bonds is going to require energy and forming bonds is going to release energy. These are all important stuff. Also, anything that changes number of collisions, the amount of energy in those collisions, or the orientation of the particles is going to change how effective my collision is going to be, which means how fast the overall reaction is going to go. I can have millions of collisions in a second, but if none of them have enough energy, no reaction. If I have millions of collisions in a second, but only 0.5% of them have the right orientation, not much of a reaction. By the way, I really can't control anything but orientation. I can make more collisions. I can make those collisions have more energy. I can't get in there and hold particles together. Okay, what are the things that can affect those rates? What are the things that can affect the number of collisions, the energy of these collisions, or the orientation? Okay, it starts out with temperature. Temperature is going to have a double effect. We'll talk about that. Concentration, if I'm talking about solutions or gases. Okay, concentration is how many things are there. Surface area, if I'm talking about solids. Now, concentration and surface area, they're going to go kind of together. Certain things I talk about concentration, other things is going to be surface area, and it really depends on the state. Presence of a catalyst. We'll talk about catalyst briefly in a couple of minutes, but we'll do a little bit more of it in class. And then the last thing is the nature of the reactant. Nature of the reactant is really simple. Some things the bond is just weaker. Some things the bond is just stronger, and there's not much I can do about that. Okay, catalyst, really briefly. Definition of a catalyst is that it's a substance is really important, that will change the rate of a reaction without itself being used up. Doesn't say anything about orientation, doesn't say anything about how it does that, but it speeds up a reaction generally without being used up. So it's not technically a reactant. It's not getting consumed during the reaction. It's also a stuff. It is definitely not energy. Too easy. Okay. Catalysts will never actually make more stuff. They'll never make the products more. They'll just make those same amount of products faster, more quickly. Okay, where are we at? This. We need to know those things about the collisions, the enough energy, and the orientation. We haven't said much about any of those things. We're going to dig into a little bit later on. Yeah, that's about it. It's going to get kind of, we'll get used to it and we'll use it up a little bit. Catalysts are still going to be one of those things that we're kind of getting used to, right? We'll talk a bit more about them, but don't expect to know everything there is to know about catalysts. They're kind of weird anyway. Talk to you another time.